자, 우리 사람 더 모일 때까지 조금 더 기다려보자. 시작해볼까? 이번에 숙제 좀 어려웠지? 괜찮았어? 괜찮았나 보지? 오케이, 그럼 해보자. So, we covered logarithms. Okay, so let's try some logarithms. I'm gonna skip around some questions because we did some in the lesson. So let's start with this question. Log base 4 to the 256. 이거 누가 풀었지? 오늘은 설린이부터 해보자. 설린아, 이거 풀었어? Log base 4.
네, I got 6.
6? Okay. Let's move on quickly. 6, I think, is correct. Let's do log base 81 of 3. 이건 도격인가 해볼까? 도경이 마이크 안 돼? 또? 그럼 유겸이가 해볼래? 이거 풀었어? log base 81 of 3.
풀었어요.
못 풀었어?
응.
오케이. 그럼 이거 어떻게 풀 줄 아는 사람? 이거 푼 사람 있어? log base 81 of 3.
풀긴 했는데 맞는지는 잘 모르겠어요.
그럼 시우가 설명해 줄 수 있어? 답은 일단 뭐 나왔어?
답은 4분의 1 나왔어요.
4분의 1? Okay.
네.
So let's try this one. We have a base of 81 and we have to the third or to the number 3. So how we solve this is we want to change it to exponential form, right? Base 81 to what power is 3? That's the question. If we rewrite it, we know that 81 is the same thing as 3 to the 4th power. So we can rewrite 3 to the 4th instead of 81. Just rewriting it like that. And if we multiply the exponents, this is our new question. Now we just set the exponents equal to each other to solve for x. So 1 equals 4x and x equals 1/4. 4분의 1 맞았어. Make sense? Hopefully that makes sense. Let's move on to a different question. Let's try log base 8 to 1 over 32. 이건 지원이가 해볼래? 지원이 있나? 못 풀었으면 민혁이가 해보자. 그럼
이거 negative 5 over 3.
negative 5 over 3. Negative 5 over 3. Okay, let's keep going. I think we're okay for this section. Let's move on to properties of logarithms. Properties of logarithms. This one is pretty okay, in my opinion. Let's try this problem. Log 2 plus log 3. 이거 하늘이가 해볼까? How do we solve this?
저 이거 못 풀었어요.
못 풀었어? Okay. So let's try this one together. We're using the multiplication property, right? And we know that it says that log A plus log B is the same thing as log A times B. Okay, knowing that, we can just rewrite this to log 2 times 3, which is the same thing as log of 6. All we want is it in this form. We don't have to get an exact number because it's going to be a decimal number if we do it. We just want it in its simplest form here. So this answer should be all that's necessary. Let's try another problem. Log 20 minus log 5. 이건 예지가 해볼래?
Is it log 100?
Log 100, okay. Close, but this time we're subtracting. So when we're subtracting, the property tells us that log A minus log B is the same as log A over B. So this time we divide instead of multiply. So in this case, it would be what, 20 over 5, right? 20 over 5, which is the same thing as log of 4. So instead of multiplying, we divide because we're subtracting. But close. Let's try one more property. It's 2 log of 4. This one's a bit more trickier than the others. 설린이가 해볼래, 이거?
Is this log 16?
Log 16, correct. So in this case, our property is that log A to the power of B is the same thing as B times log of A. So we can take the exponent and bring it out front. So in this case, since the number is already out front, we can move the exponent we can move the number to an exponent. So we can rewrite it as log to the 4 to the second power, which is the same as log of 16. Correct? Okay, any questions on this part, or can we move on? No questions? Okay, let's move on. So the next thing we covered is the change of base rule. Change of base rule. Let's try log 2 of 1234, or 1234. 이거 유겸아 이거 풀었어?
아니 저는 주말에 밖에서 계속 자가지고
그래?
숙제를
숙제를
못했어요.
못했어?
네.
그럼 지원이가 이거 해볼까? 아니면
Eagle, like I got it, but I wasn't sure if
Okay.
mine was the answer.
what did you get?
I got like 10.
10. Okay. Let's try this one. So the change of base rule tells us that we can rewrite this whole thing as log 1, 2, 3, 4 over log of 2, both with base 10, but we don't really write the base 10, right? So from here, we can just plug it in our calculator and solve it. I don't have a calculator with me right now. Log 1, 2, 3, 4 is around 3.09. Log 2 is 0.3, around 0.3. So 3.09 over 0.3 is, yeah, around 10. It's around 10. Yeah, 10 is accurate enough. So yeah, it should be around 10. I got 10.3, but if you got around 10, that should be correct. Let's try one more problem. Let's try 3 times log base 9 of 1/12. So for this problem, 이거 시우가 해볼까? 풀었어?
minus negative 3.393.
Negative 3.393. Okay. Did everybody else get this answer?
I got it.
Okay. Nice. Let's just move on to the next section then. Actually, we have 2 multiple choice questions. The first one says, which of the following is equivalent to 1 over log base b of 4? And we're given 4 choices. What did you get, 민혁아, for this one?
이거 I got B.
B? Okay, B is log base 4 of B. Okay, did everyone else get B?
Me, but I don't. My sister helped me.
Okay. So, this one. I solved this last week too. Let's see. Log base b of 4. So, how should we solve this? Wait, so how did you guys solve this? I kind of forgot how to solve this as well.
I also saw it in a logarithm. Rules and stuff that said if you like divide it, you just like twist it around and like change the exponent and the bottom thing.
Oh, really? So
It's just like a rule, I think.
Oh, interesting. So if you divide by something, you can rewrite it as just this.
Yeah,
Okay.
that's what I saw on the site.
That's an interesting rule. I did not know that. But there has to be a proof, right? So I guess you can just follow that rule. 민혁아, how did you solve this one? How did you get B?
이거 그냥 약간 찍은 거긴 한데 그 원래는 분수였던 게 그냥 이렇게 바뀌어버리니까 왠지 이렇게 될 것 같아서.
Okay. I mean, that's a good guess, I guess. Oh, right. I think if you rewrite this as 1 divided by log base b of 4, we can use this as a change of base rule. So 1 log 4 over log b, right? Yeah. And then if you're dividing by something, it's the same as multiplying by the reciprocal. So it's 1 times log b of log 4, and which is the same thing as just log b of log 4, since 1 multiplied by something isn't right. And from here, we can do the change of base rule, except the opposite way around. So the change of base rule says log a to the b is log b over a, log b over a. And here we rewrite it as log, what is it? 4 to the b, because we're coming from this step, this step. Yeah, that's how you said it, right? And that was something we covered last lesson as well. You guys might have forgot, but it was other multiple choice where we had log base 7 to the a times log base b to the 7. For this question, we used the change of base rule for both logarithms. So we rewrote it as this, and we can cancel the log 7s out, and we're left with log a over log b. And once again, we can use the change of base rule to write that this whole thing simplifies to this. So for the next multiple choice, your answer should have been D. Hopefully everyone else got D. Let's try solving exponential equations. Solving exponential equations. Okay. So we're given one main equation for all the problems, 7 times e to the 0.1 t equals 47. Let's try part A. Solve the equation for t. Express the solution as a logarithm in base e. So who was able to solve this one? Hanera, were you able to solve this problem?
Not really. Sorry, I kind of had trouble with logs.
Okay. So let's take it one step at a time. Our first step is to get the t isolated, right? That's how we solve for t. So we can divide 7 by both sides. And our second step here is, we kind of covered this last lesson. This is a hard step, but if you multiply log base e on both sides, so do log base e on this side to get 0.e1t, and do the same on the other side. We're allowed to do that, right? Because if you do something on one side, you have to do it on the other side. And from here, we have a case where we have an exponent. So if we take the exponent outside, using one of our properties, we can rewrite this whole thing as log base e to the e power over log base e to the 47 over 7th. Okay. One other rule is that if we have a base and this number is the same, it's the same thing as 1. So we can just cross that out, leaving 0.1t on one side. So we just divide by 0.1 on both sides, leaving log base e 47 over 7 all over 0.1. Can't really simplify that any further unless you have a calculator and you want to write it in a decimal form. But in a base E format, that should be our final answer. Anybody have questions on this? Nobody? Okay. I'm gonna skip the word problem part. Hopefully you guys did okay on that, but I'm just gonna call the homework a day for right now. Do you guys have any final questions on the homework that you want me to go over, or anything that was confusing? Nothing? Okay. So we're done with logarithms then. We're gonna do transformations. Transformations of functions. Has anyone heard of this? What transformations are?
Not
Nobody?
really.
Not really? Okay. Well, what do you think transformations are? Just by hearing the word.
Changing.
Changing, right? We're changing the function. That's exactly what we're doing. So there's 3 types of changing. One is just translation, or moving it up, moving it down. You know, we can shift the function, shift. Another is reflection. So we can reflect it like over the x-axis, over the y-axis, over the origin. But there's reflection, and the final one is shrink or stretch, which I think is the hardest one. But let's cover them one by one, first of all. So we're first gonna talk about translation, which is translation. That's number 1 of transformations, of all transformations. So translations are pretty self-explanatory, whatever. Yeah, they basically mean what you think they mean. So if we have, let's say, actually, let's draw this graph. Y equals x. A translation of this function would be something like this. Y equals x plus 1, where we move the function up 1 step, or one interval. We're not changing the function, the shape of the graph, where it's a straight line, but we're moving the graph. That's what translations are. So we can either move it up or down. In this case, we moved it up 1 unit, right? Or we can move it left or right, left or right. So this example is pretty easy. To move it up or down, we just add numbers, right? X plus 1, we move it 1 unit up. X plus 2, it would be something higher. X plus 3, it would be even higher. And vice versa, if we do x minus 1, it would be below the graph, below the origin, so we would move it down. X minus 2, it would be even further. -1, -2, etc., right? Moving it up or down is pretty self-explanatory, but how do you guys think we move it left or right? Any thoughts?
Add a number to the y.
Add a number to the y, okay. So if we have a number y equals x squared, okay, since we added a number to the x to move it up or down, +1, -1, how about we add a number to the y? Okay, that's actually a pretty good thought, but it would be the same thing as moving it up or down, because, for example, this graph y equals x squared, if I added a 1 to the y, I rewrote the equation. it would be the same as just moving it 1 unit down, right? So we're not adding one number to the y, but you're thinking very correctly. So how we move it left or right is we add a number to the x, but only the x. So what I mean by that is y equals x squared. How we moved it up 1 unit and down 1 unit is we added 1 to the whole function. This is a function, so we added 1 to the whole function. So the whole function shifted up once. And if we subtracted 1 to the whole function. But if we only add x, add 1 to only the x, so y equals x plus 1 squared. So we're literally substituting x for x plus 1. So for every x we see, we delete it and write an x plus 1 instead. We're adding 1 to the x. So in this case, it's x plus 1 squared, except in parentheses. So if we add 1, do you think it's going to go left or it's going to go right? Right now, we have y equals x squared. Left or right by adding 1 to the x? Well, we would think that adding 1 would move it to the right, right? We would think it would move like that. But actually, when we shift it left or right, it does exactly the opposite. So if we add 1, it goes to the left 1 unit. But if we subtract 1 unit, so we write y equals x minus 1 squared, then it goes 1 unit to the right. Anyone confused so far? Or does that make sense?
That makes sense.
Okay. So let's try an example. So we're going to work with absolute value functions since it's easy to see the translation when we do that. Absolute value functions look like a V. Yeah, they're pretty self-explanatory. So we have a graph here. And the graph is an absolute value function. Y equals absolute value of x. And somebody changed it and the graph shifted 2 units right and 3 units up. So the graph changed to this graph. 2 units right and 3 units up. What do you think the new equation would be of our absolute value function when it shifted 2 units right and 3 units up? Any thoughts?
Parentheses x minus 3, parentheses and plus 3. Wait, I'm not sure.
Okay. Let's try this. Okay. So first of all, let's do it went up first. Let's do the raising up and down first because that's easier, right? So it went up 3 units. So what do? Well, we add 3 units to the whole thing, right? Our equation is pretty small. So just adding 3 units to this is just plus 3. So if we add plus 3, it went up 3 units, 3 units up. So right now, if we graph it, our absolute value function looks something like this, where it's up 3 units. We haven't shifted it 2 units to the right yet. So now how do we do this? Well, 2 units to the right isn't plus, right? It's minus. So instead of x, we write x minus 2 for every x we see, because we know that it shifted 2 units to the right. X minus 2 is going to be that. And we just keep the plus 3. That is our final equation. If we add the x minus 2 there, then our equation shifts 2 units to the right. Voila. Pretty simple, right? Let's then try. Okay, let's try. One more example. So let's try an example where we aren't using absolute value. Let's say we're using x cubed. So y equals x cubed, and our question is, when is the vertex? No, not the vertex. The 0 of the what do you call it? This point, this middle point. Yeah. This, I'll just call it a climax. The climax of the function shifted from 0, 0 to -4, 1. So what does this mean? It was at 0, 0 here, but then it changed to 1, 2, 3, 4, and 1 unit. It changed to this point. So how should we tackle this? Well, this time let's do the left to right first. And if we know that it went 4 units to the left, which is the same as +4, right? So instead of x, we write x plus 4. So it's x plus 4 cubed now, but we haven't raised it up 1 unit yet. And this is our whole function, and we just add 1 unit to the whole thing. And that's our final function. Any questions on this so far? Do you guys get how to shift graphs to the left, to the right, up and down?
Yes.
Okay. So as we do transformations, you guys are going to see a pattern, okay? I want you guys to see spot what the pattern is. So we're going to do reflections this time. Reflections are also pretty easy. If we're given, let's say, a graph, let's say that's y equals x minus 2 squared. So from here, it shifted 2 units to the right, okay? And we're said that this equation reflected over the x-axis. So this whole thing became like this. It flipped over. Well, who has a thought on what the new equation would look like? What do you guys think the new equation would look like? No thoughts? Okay. Well, we kind of talked about this in the beginning. But if I just add a negative there, do you guys think it would flip over, right? If I add a negative, then the whole function will flip over the x-axis, okay? So it will flip from up to down. But what if I want it to flip from here to here. So this time it flips over this line, over the y-axis, not the x-axis. Well, in this case, it's the same. We don't add a negative to the whole function. We only add it to the x. So our equation was y equals x minus 2 squared, right? So instead of x, this time we just write negative x. For every x we see, we replace it with a negative x. So if we rewrite it as this equation, then this graph will actually reflect over the y-axis into this point. That's basically it for reflections. But let's try one example problem. Let's say f of x is given as negative 2 log base 2 of x plus 1 plus pretty intimidating. So what this looks like is, it looks like, that's 3, looks something like this. That's our equation, or we're shown this part of the equation. And we know we're searching for what graph of g of x is. We want the equation. And we know that the graph of g of x looks something like this. Okay, so just by looking at the graph, we can tell that the graph of f of x, reflects over the y-axis. So this axis, it flips over, right? So what do we do if it flips over the y-axis? What's our step?
In
right?
front of x. In front.
Right. We write a negative x instead of an x. We give a negative to every x we see. So from here, we don't really have a negative. And inside the parentheses, we find one negative. And so we just add a negative to the x. That's really all we have to do. The reflected function is going to be this long thing. And the only change you see is from the positive x to a negative x. But what if I told you that g of x isn't this graph, but it flipped over like this? So in this case, it flipped over the x-axis, not the y-axis. So what's our step if it flips over the y-axis? I mean the x-axis.
A negative outside the parentheses.
Outside the parentheses, the important thing is to put a negative over the whole function, right? So we can actually just write it as this, negative 2 log base of x plus 1 plus 3, another parentheses. So we're multiplying a negative to the whole thing. So if we just rewrite this, negative times negative 2 is going to be just positive 2, right? This whole thing doesn't change, but at the end, positive 3 changes to a negative 3. Can you guys see that? Yeah, that changes to a negative 3. So we're changing the sign for everything, for every monomial when we multiply a negative. So if we switch it over the x-axis, that's our equation. Does anyone see the pattern so far for transformations? Nobody? Okay. So we're gonna do the hardest part of transformations, I think, are the hardest. Shrinks and stretches. So from the two previous examples, we never really touched the graph. We only moved it around and reflected it. The actual graph didn't change shape. But now we're gonna make it change shape. So for example, if it's a y equals x squared, can we make it like what? Wider, or can we make it more narrower? That's what shrinks and stretches are. So there's two types of shrinks and stretches: vertically shrinking and stretching, and horizontally shrinking and stretching. So let's do vertically shrinking and stretching first. Vertically shrinking and stretching. Okay, we have a graph y equals x squared. If I say I want to vertically stretch this graph, does anybody have a thought on what that means? What do you think I mean if I say I want to vertically stretch this graph? No thoughts? Okay. Well, we know vertically means this way, right? Up or down. Stretching means to elongate, to make longer, right? So vertically stretch means we want to make this graph longer, but like this. You see how we're kind of stretching it vertically? So if we had like one hand here and another hand here, we're like pulling the graph from up and down. So, oh, is this a good analogy? So we're pulling the graph up and down, but vice versa. If I say I want to vertically shrink this graph, what do you think this means? Well, in this case, we don't want to stretch it so it becomes longer. We're shrinking it, right? So we want it to be vertically short. So this time, these two hands are pushing down. So you're pushing down on the graph. So it's becoming flatter. Makes sense?
Yes.
Okay. It might feel easy at first, but when we get into equations, it's actually pretty difficult to figure out if it's a stretch, shrink, blah, blah, blah. Yeah. So as of right now, let's do absolute value. So we're given an absolute value function, y equals absolute value of x. No, not y, f of x equals absolute value of x, okay? And g of x, as we know, is this function, okay? This function right here. What do you guys think the new function would be? The new g of x function, if we rewrote it? Hard, right? Well, we're pushing it down. So we know that we're vertically shrinking it, right? So if we're vertically shrinking it, then, I didn't explain this. So when we shrink or stretch, we do it by coefficients. So we multiply a number to the whole thing. So if it's x squared, then we would multiply a number a. Okay, and that would make it either longer or wider, etc. So in this case, if we're vertically shrinking it, our a, or our number that we multiply it by, always has to be less than 1. So absolute value of x is the same as 1 absolute value of x. So if we're shrinking it, we're multiplying it by something less than 1. In this case, it's half, because, well, I mean, it's pretty, you visually, this is half of what it was originally, right? So we're multiplying it by half. So our new function is half multiplied by absolute value of x. So important thing to remember, vertically shrinking is absolute a less than 1. On the other hand, vertically stretching, if it's not a less than 1, it has to be a greater than 1, right? So if we have a absolute value function and we want to make it longer, like that. Wow, that was really badly drawn. Hopefully you get that. That's by a factor of 2 this time. So it becomes, from this, it becomes y equals 2 times absolute value of x. Okay? Anybody confused so far? Or this makes sense so far? Because we're gonna do something harder then. Okay, so this time, horizontally stretching and shrinking. Horizontally stretching and shrinking. So horizontally stretching and shrinking is kind of similar to vertically stretching and shrinking, but also kind of the opposite. So if I was to horizontally stretch this, stretch y equals x squared. This time our hands are not on the bottom and top where we either pull this, like crunch this, or we crunch that, or we pull it. But this time, imagine your hands on the sides of the graph. So horizontally stretching it is you're pulling your hands back. So this graph becomes wider. Okay? But if we horizontally shrink this, this time we're pushing. Oh, this arrow was wrong, by the way. It should have been that way. This time we're pushing on the graph, right? So from this, it becomes longer. That's what a horizontal shrink is. But, okay. So when we horizontally shrink, let's do stretch first. Stretch. And we have a function, say it was like that. And this function became something like that. So we see that this function, if this was a dotted line, this is our transformed function, it became narrower. So it became a horizontal, not a stretch, a horizontal shrink, okay? And when we horizontally shrink something, a is less than 1. On the other hand, same thing. If you have a function, if you horizontally stretch something, so it gets longer on both sides, then horizontally stretching is a is greater than 1. Wait, no, this is a is greater than 1. And this is a is less than 1. Wait, horizontally stretch is less than 1. My bad. So we have these 4 units now. When it's vertically stretching or horizontally shrinking, it's a is greater than 1. And if it's horizontally stretching or vertically shrinking, it's a is less than 1, right? But the question is, how do we know if it's a horizontal shrink or a vertical stretch? So if I gave you a graph, let's do y equals x squared, like the same. And I said that the transformed graph looked like this. Well, this could be a horizontal shrink, because if you think about it horizontally, these 2 hands are pushing it together, right? They're clamping it down so it becomes longer. But if we think of it as a vertical stretch, it's the same thing. We imagine hands here, and they're stretching the function. So how do we know the difference between those 2 things? In this case, the answer is they're the same, but there are going to be circumstances when they're 2 very different things. I drew a graph to explain that a while ago. So I drew this graph and this graph. So in this case, this is our f of x, and this narrow thing is our g of x. What do you guys think? Do you think this is a vertical stretch or a horizontal shrink? Any thoughts? No thoughts? Okay. In this case, this is going to be a horizontal shrink and not a vertical stretch. Why? Because horizontally, these digits changed. What I mean by that is, if you look at this vertically, the graph didn't really change. But if you look at this horizontally, it changed. If this graph was y equals negative x minus 3 squared, per se, then if we're horizontally shrinking it, we're adding a coefficient. Oh, I didn't explain this. Only to the x. That's our pattern, okay? That's the pattern for our transformations. When we move it left or right, we add it only to the x, but if we move it up or down, then we add it to the whole function. So similarly, if we vertically shrink it or stretch it, which is up or down, then we multiply the coefficient to the whole function. But if we're multiplying it so it shrinks left or right, then we only do it to the x. So in this case, we're horizontally shrinking it. So let's say we added a 2 instead, okay? So if we look at this example, we know that x went 3 units to the right, but in this case, x may went 3/2 units to the right, so 1.5 units. So it only went this much, whereas in this case, it was usually this much. If it was a vertical stretch, you'd have multiplied something like -½ to the whole function. So it would have been something like this. And x would still have moved 3 units to the left. So if we multiplied half, it would look like this, and it wouldn't be shifted. Confused? Or did that make sense? Wow, so you guys got that. Wow, okay. So I didn't really explain horizontal shrinks and stretches that well. So one last recap is when we're horizontally stretching or shrinking something, we multiply a only to the x. So if it's x squared, then our transformed function would be equals ax squared. Whereas if it was a vertical stretch or shrink, it would be g of x is a times x squared. You see the difference? In this case, it would be a squared times x squared. But in this case, it's just a times x squared. Any last questions on transformations? Or does everyone get transformations?
Kind of.
Kind of. Kind of. Okay, that was kind of uncertain. So I guess you guys don't have any last questions. It's your last chance. So just to clarify one thing, not clarify, something you have to memorize. If we're moving it left or right, we only do it to the x. We only do it to the x. But if we're moving it up or down, we do it to the whole function. So we do a times f of x. In this case, we only do a times x. Well, not really a times x. It's more like it's f to the ax. Yeah. Make sense? Okay, that's it for today. I'll post
Thank
the
you.
homework on Classroom. Yeah, good luck.
Thank you.
Thank you.